second-class to other type, or is it just a mix of materials that makes it?
I would say there's a couple of different.
There are two or three different families of materials. So they have common feature in them is that they all contain iron. But then again, how ubiquitous is that? Maybe one day you would be able to make it without iron, but let's say with nickel. The point being that they have some structural similarities.
They're all layered.
So they're all layered, and the certain arrangements of iron atoms in these compounds is similar between the different materials. But if you count all of them, there is probably a good 15 or a good dozen of these materials. So I wouldn't say it's only one or two. There are more, but you can kind of classify them and say, well, the cuprates are like that, and these guys are like this.
In terms of the hot things, I guess I would also say there's kind of some things that are hot in the sense that there's lots of papers coming out about these topics. Like you can argue whether they're really condensed matter physics or not. So the field that has now acquired the name plasmonics, which looks at plasmons are collective excitations of the electronic fluid in a metal. So there's sort of if you think of the electrons like the liquid in a pond, plasmon excitations are like the ripples on the surface of a pond. Right? You bang on a piece of metal the right way, you get the electrons to slosh around. And they're basically incompressible fluid for a lot of practical purposes. And so these people have gotten very, very excited on more, it's sort of the photonic, electrical engineering edge of condensed matter. People have gotten very excited about this now I think for two reasons. First of all, the technology to study these things has gotten cheap enough that a lot of labs can do it now. And secondly, I think the computational power that you can get has gotten good enough that lots of people can do at least simplified calculations. And so just, it's sort of physics for the masses, right? I mean, if lots of people have the capability to look at something, it almost automatically becomes more popular.
Going back to the subject of high temperature superconductors, since we have both experimental theories here, could you say what are the limiting factors from either side? Why haven't we found it yet?
The mechanism?
Why haven't we found the mechanism and the higher
And what is a typical high temperature?
100 Kelvin is the high end of high temperature.
Is that under pressure?
Ambient. I mean, what's the highest ambient one?
12 or something. In the cuprates it's 120, 130. It's the Hg, the mercury. The mercury-based compounds.
Yeah.
So they have quite complicated structure, similar to what's known as a bismuth, but they have, instead of bismuth, they have mercury. So they're kind of highly toxic, they're difficult to manipulate, but just for the record, they're the ones that follow the record for the TC.
So, I mean, so these things are structurally very complicated. Very often the materials with the best superconducting properties are ones where their stoichiometry is not terribly well defined. So you'll have, when people talk about the yttrium barium copper oxide, the actual optimum oxygen stoichiometry is like a non-integer number of oxygens in that formula. So what this means is, as a practical matter, is that these things have a lot of disorder in them, and they're very challenging to make and grow. Large single crystals are a very useful thing if you want to study them, because again, you want to knock the number of parameters you can't control as low as possible, right? So large single crystals are nice to get. It took a long time before people figured out how to really grow good single crystals of some of the cuprates. And they're very complicated materials where there's lots of pieces of physics going on, and the questions that people get into arguing about are, for example, are these two tendencies in the material like competing with each other, or are they helping each other out? Or, so these materials have, I think everyone sort of agrees. If you're really interested in this, there's an issue of Nature Physics from 2006 where they sort of summarize the state of the field in 2006. And they go around and they ask a whole bunch of theorists and experimentalists, like in one paragraph, what do you think is going on, and what do you think the roadblocks are and stuff. So, but I mean, it's really, the materials are so complicated. I mean, I think socially one of the problems that happened is certain theorists liked certain experiments because the results aligned well with their pet theories. And so you would end up with people sort of talking past each other saying, well, my experiment shows X. so it's got to be this. And someone else will say, well, my other experiment, which is a different experiment on a different but related material, shows this other thing. And that's consistent with my views, so people will just argue. It's just a hard problem.
I mean, so I totally agree with what Doug just said. Unlike graphene, it's very difficult to then write the Hamiltonian that you want to start with. So the system is not clean in the sense I don't mean the impurities. It's not clean, but it's not very well posed. Now, for worse or for better, that's how most of the problems are in condensed matter. I still remember one of the first problems that my PhD advisor gave me. We had an hour discussion in his office, and by the end of it, so he described the phenomenology, and he told me what was observed in the experiments, and this is what would be an interesting question to answer. I says, right, but can you write down the Hamiltonian? And he looked at me and says, well, notice, I haven't written the Hamiltonian at all, and there is a reason for it. A, because I don't know. B, because by writing your own Hamiltonian, I don't want to put you off track. So often the situation is like that. But more seriously, coming about the high temperature superconductors. I think what ultimately, from the serious point of view, seems to be a bit discouraging is that it's very hard to put a criterion on what you call a theory of high temperature superconductivity. By this I mean that there have been a lot of experiments, and when you say you have a theory, does it mean it agrees with some of the experiments, or does it agree with all of them? If it's a subset, then which subset of experiments? And I still recall when in 2005, the STM experiments have found on the surface of the cuprates what became known as a checkerboard pattern. So the checkerboard basically means in that case is that you have a bright, dark spots aligned just like on the checkerboard on the surface when you look with the scanning tunneling microscope. Now, immediately in the session of the March meeting, which was in March same year, I've heard 3 theory talks. So there were 5 talks total. There were 2 experimental talks, and there were 3 theories. Each of them, the theorists, basically jumping and saying, hey, my theory must be right because I can explain this. Now the trouble was all 3 of them could explain this. None of them predicted it before the experiment, but all of them could post-dict and say, oh yeah, we can explain this. So then you look at these 3 theories, which look very different from each other, and you wonder which of them is right. Maybe to phrase it differently, at some point, we had a visitor, when I was working in Canada, University of Sherbrooke, we had a visitor coming from Yale University, Steve Gervin, and at some point over lunch, I asked him what he thought about the theory of high temperature superconductivity. So he joked and says, you know what, I think I once had a dream. It was a nightmare. So my worst nightmare was that at some point I do the right calculation and discover the true theory of high temperature superconductivity. And then I'm giving this talk and there is this huge audience. And as I'm writing my theory, somebody stands up, actually 2 or 3 people stand up at the same time. Yes, but I said it before 10 years ago. So this is the trouble you have, is that even if one day the theory is discovered, it's probably going to be very contentious as to who had the right description, and even forgetting about the personalities. Just knowing what is the right ingredient and what is not is very hard.
I mean, on the physics side, let me give an example from my own research of a tangentially related problem. So one of the things we've studied in my lab in recent years is a material called magnetite. You've probably all heard of this. Magnetite is iron oxide. It's this lodestone, right? It's the stuff that ancient mariners used to magnetize compasses with. Magnetite is a simple compound in the sense that it's Fe3O4. That's it. Stoichiometry is well known. You can grow single crystals of it. It turns out it's an example of a strongly correlated transition metal oxide. It turns out that this ignoring electron-electron interactions is a bad idea in this material because if you do that, you think it should be a metal, and it's not a metal. turns out. It has very interesting properties, and people have been arguing about the nature of the ground state for this material for 70 years. Okay. And I mean, really arguing. And these include people like Anderson and Mott. I mean, these big name people have thought about this problem. And one of the essential piece of physics that's relevant there that is also, that I think encapsulates what's going on in some of the ITC stuff. So people are, what is the small parameter in this problem? If you want to write a model Hamiltonian, you want to throw away the stuff that you're allowed to throw away and still retain the essential physics, right? So you look at this problem, you say, okay, the electron-electron interaction is small. No, I have to keep those. The exchange interaction that gives me magnetism, is that small? No, I have to keep that too, because it's magnetic. The electron-phonon coupling, so how the motion of the lattice, is that small? No, I kind of have to keep that too, because I know that there's a structural phase transition in this stuff as well. And so in the end, there is no small parameter. Nothing is small. Right? All of the energy scales of the problem are about the same size. And so they're all fighting with each other. And you run into that also in the ITCs. I mean, there's issues with magnetism, and there's issues with on-site repulsion and hopping integrals. And I mean, there's all these interaction and energy scales in the problem, and it's hard to neglect too many of them. And that just makes it a tough problem. As for, I find it hard to believe that we've actually, in just the brief period of time since ITC was discovered, that we've zeroed in on the universe's physical maximum for TC. That just seems unlikely. So, I don't know. I mean, there are people who argue that the real mystery isn't why is TC as high as it is. The real mystery is, given some of the energy scales of the problem, why isn't TC much higher? So, I don't know where it's.
Would it be accurate to say that superconductors were just kind of accidentally discovered?
Originally, sure. Yeah.
Well,
so is it more of a sort of chemistry approach to?
Well, they were looking for something.
Although Bednorz and Muller had superconductivity in their head. The original superconductors were discovered by physicists, not chemists. They wanted to know what happened if we, it was Kamerlingh and Onnes, the guy who invented how to liquefy helium. And there was a big question about what should the electrical resistance of metals do at low temperatures. And so he liquefied helium, and he worked with mercury because it was one of the most pure metals you could get, because it was a liquid and you could do all this distillation stuff to get it really clean. And he found, there was a great article in Physics Today a few months ago about this. He found that the resistance vanished around 4 Kelvin in mercury, and that was how superconductivity was discovered. But I mean, and now what were the Japanese? What was Hokono? What were those guys looking for when they did the iron nuclides?
Well, let's see. I think they were basically looking into their chemists, and they were looking into the chemistry of the intermetallics. I think that was their motivation. In fact, the first compound that they discovered had a TC of like 8 Kelvin, I think, or 3 Kelvin, I don't recall. And they noticed almost as a post-thought in their paper. Nobody really paid attention for about a year, until they managed to make a sister compound that somehow had a temperature of 26 Kelvin, and that's the paper that's now quoted as a discovery of the iron nuclides. Why 26 was more significant than 3 or 8? Well, because for a long time there was this the thought was that if conventional theory of superconductivity is correct, if it applies, meaning that the attractive interaction between the lattices is mediated by the phonons, meaning by the vibrations of the lattice, then knowing what in a typical solid the vibrational frequencies are kind of limits as to what kind of temperatures you will get for superconductivity. And the universal answer, of course, it depends on the material, so you can't really, but by and large, by the 1970s and 80s, people thought that the temperature would be of the order of 30 Kelvin. In other words, 30 Kelvin was considered a kind of limit where A, none of the compounds known had TC higher than that, and B, they were all known as electron-phonon mediated, so there was no question. So when this compound was discovered, and it was by 26, and then within a couple of months it became 52, people have immediately realized that something very interesting is going on.